in this chapter don't show up on the final and will get discussed in much more depth in 151. Okay? So if you have to take 151, you'll learn more about gases. If, for heaven forbid, you move up into physical chemistry or inorganic chemistry, you might have to spend a whole lot more time with the gas concept, and I'm sorry, but I pity you. Okay? Because that's rough. Oh, and I was recording. Dang it. Properties of gases. Okay? So we get mainly 4 properties. Your textbook says 5. I think 2 of them are ultimately the same. So there's 4 main properties of your gases. They have a variable shape and volume. So when we look at an individual atom or a group of atoms that are in the gas phase, okay, they will fill whatever volume is trying to contain them. Whereas if we took a solid or a liquid, that is going to be determined based on the solid or the liquid, whatever volume they contain. Okay? The liquid will kind of be amorphous to whatever the bottom of your container is, okay? But it's not going to fill the whole thing. So for instance, you take a bowl and you put a couple milliliters of water in it, it doesn't fill all the way to the top of the bowl. Right? Whereas if we did a gas, what happens with a couple milliliters of gas? That's going to fill the space of that container. Okay? One of the nice approximations that we'll make is that they expand and compress uniformly. Okay? This process is where you get the 2 rules that they were talking about. When you're looking at expansion and compression, ultimately to me those are the same things. They're just opposite directions. I don't think that deserves a second bullet. Okay? And what we're saying by this is that they will always move in very uniform fashions. That's ultimately because our gas particles are so far away from each other that they very rarely interact with each other. Which means if we expand the gas, all it's going to do is fill the rest of that void. Okay? If we then compress it down, they're going to then shrink down so they get closer to each other. Okay? And they will do that in very uniform fashion. We don't get this weird shifting action that we could potentially get with a liquid or even a solid. Gases have very, very low densities. What does that mean? There's lots of space between molecules. So for a given volume, what is the mass of a gas in comparison to a liquid or solid? A lot lower. Okay, so there's very little mass within that volume. That's ultimately what we're saying with our densities. The other big one is our gases will mix uniformly in the same container. So if we have different gases, they also interact uniformly throughout the whole thing. Okay, which kind of goes back to rule 2. If we take an individual gas, it's going to expand and compress uniformly with the same particles around it. If we throw in a different particle, it doesn't matter. It's still a gas. You're still going to get that exact same kind of interactions. Okay? Evenness throughout the whole thing. This means when we look at mixtures of gases, what type of mixture do we have? Heterogeneous or homogeneous? Homogeneous. Those gases will spread evenly throughout the entire volume. There is no separation of them. So we get a homogeneous mixture with our gases. Okay? One of the extra things that can be kind of interesting to think about here is that gases do exert a force, okay, which does seem a bit odd. When we go walking through the air, or walking around, we don't really feel a force pushing against us. There is one. Okay? That force becomes more relevant when we think about, say, windy days. What happens on a windy day? Okay? You can get pushed around by nothing. Okay? That force is what we're going to end up spending, or what the initial probably observations came from when people started studying gases. So what is this invisible force pushing against me? Where is it coming from? How can I describe it? Okay? Because they couldn't see atoms or molecules. As far as we thought about way back when, is that we're walking through nothing. There is nothing in the way. That's why I can move so freely. Okay, and dance. Okay, poorly. So, a couple things we now want to push a little bit further is ideal gases. Okay, so we want to look at a couple of these things a little bit closer. Gases have variable shape and volume. Okay, and we address that. One of the kind of subtleties that come out of that is that each particle, or one of the approximations that's going to come out of that, is that each particle has no volume. Okay? And we kind of have to make that assumption for a lot of these other things to work for us. Okay? So well, let's think about it. Does that assumption make sense? Okay? If we look at the volume of an individual container, say 1 liter or a 2-liter bottle, okay, and I add a single atom of gas, did the volume change? Okay, think about on really, really, really small scales. Okay, it does change. If we take a look at a container, let's draw this out real quickly. We got a little box with our container in it, or our container with nothing in it. And it's going to have some volume. If I now put my particle in here, and let's do it for an extreme case, let's say my particle is this big. Can that particle move through the exact same space as it had previously? No. It can't move through the space that it's already occupying. So the volume that that particle is now in is a little bit smaller. So when we look at large particles or small volumes, this rule doesn't work out for us. But when we look at relatively large volumes, what's the size of our particle? Can't even draw it. A single dot. Okay? It's now approximative, saying that it's not changing the volume of the container. Okay? Where this becomes a little bit more understandable maybe is if, let's take a look at 2 particles. Okay? Let's go back to our 2 particles floating through this container. Is the volume different? Yeah. Particle number 2 cannot exist in the exact same space as particle number 1, which means the volume must be different than it was initially. What happens if we now make those particles very, very, very small? That's still true. Particle 2 can't exist in the exact same space as particle 1, but how much of a volume reduction was there? Relatively very, very little. Okay? So what we are doing is simplifying our calculations, or simplifying our thoughts, so that we can make the calculations easier. Okay? It is an assumption, and it does have cases where it becomes invalid. What happens if instead of looking at a nice big space, we look at a very small space? Okay? Now that particle volume does matter, but in most cases it does not. Okay? And that's going to help us explain a lot of the calculations that we go through and do. And that's why we look at, when we talk about gases, ideal gases. And in the ideal circumstance, our particles do not take up space or do not have a volume. Yes?
Volume's length times width times height. Volume
Yes.
of the chamber never changes. Your density of the gas changes.
You're right, the volume does not change. Let's say we take a look at this particle. It can move completely within what volume? Let's say inches.
2 to the 3rd power.
It's only a square, but
8 inches cubed.
okay, if we made it cubic, that's going to make it look more difficult. Let's stick with a square. Okay, if we stick with a square, what's our volume? 4 inches squared, where that single particle can exist. If we put in a second particle, can that second particle exist in the exact same spot as our first particle? No. That volume is now occupied. It cannot be at that point, which means what happens to our volume of the container now for these 2 particles? The available volume goes down, and that's what we're concerned about when we run our calculations. We have to be concerned where our particles can move. If where they move changes, then we have a different calculation that we'd have to account. When they're small particles, that change is minuscule. Instead of it being 4 inches cubed, or squared, we'd have 3.999999 inches squared. Okay? As far as sig figs go with our calculations, no change. What happens if we make those particles much, much larger? Now what happens to the possible space, or the possible volume where that particle can exist? Now, instead of it being 3.999, it might drop to 3.5. that is now a substantial difference. That is going to affect my calculations because that particle can't exist in that volume space. Okay. So it is kind of a tricky concept to wrap our heads around. Realize that our approximation is that it has no volume, and that simplifies our calculations drastically. Okay. I cannot emphasize how much simpler that makes it. Okay. We use that approximation, actually, in this next process. 1 mole of a gas is equal to 22.4 liters. Okay, well, what gas? Any gas. Okay, well, what happens if I change from hydrogen to iodine? Take a look at hydrogen versus iodine gas. Does anything change? Okay, think about it in general. Okay, if we look at a hydrogen atom or a hydrogen molecule, gas molecule, H2, versus an iodine molecule, does anything change? The size of the molecule changes. So if we took a look at our hydrogen, it might be something like that. Okay, not a big deal. What happens when we move to iodine? Are they taking up different volumes? Absolutely. If they're taking up different volumes, if we take the same number of those particles, should they occupy the same volume? No, because the iodine takes up more space. Okay? What ends up happening? When we look at gases, it doesn't matter what particle we're looking at or what gas we're looking at because of our approximation. We assume that our hydrogen molecule and our iodine molecule take up the exact same volume. Okay? With that assumption, if I take a mole of them, what's going to be the volume? It'll be the same regardless of what molecule I'm looking at. That approximation is huge because that gets us this relationship. A mole of any gas will occupy 22.4 liters. Okay? And that's because when we look at gases, we're saying that those atoms or molecules are so far away from each other that they don't interact, that we can then say that by the time one molecule wants to move into the space where the other one was, it's already moved. So effectively, our volume stays constant through the whole thing. Oh. Okay. This approximation, it is still officially an approximation, okay, is massively important. Why might this be massively important? Can I convert the mass into moles? How do I convert mass into moles? Using that? Where's mass in that equation? That says moles and liters. Where do we convert mass into moles? The periodic table. So if I'm given a mass, I can convert that into moles. What can I now do with that with this new conversion factor? I can convert it to a volume that that species now occupies. Okay? So it introduces a way to convert between the number of something into a volume. This conversion factor will show up on your exam. You do get directly tested on this. Okay? This is something that came out of Chapter 8, and I have no idea why they dropped it in Chapter 8, because this is specific to gases. What happens if we looked at a solid? Would we expect solids to occupy the same volume? No, and that's because solids interact with each other. Okay? They have very strong attractive forces. We have to address them differently. This equation is known as your molar volume. Okay? Just got to cover that. So what does that STP mean? Because it says that this equation is only true when at STP. And officially, it's not even just when it's at STP. It's when we're looking at an ideal gas. What if the gas isn't ideal? This equation doesn't work either. Okay, so what does STP mean? Standard temperature and pressure. Okay, that's a fun statement. What do you think the standard temperature is? Okay, this is one of the reasons why science can be a pain in the ass. If you take a look at STP and you talk to an engineer versus a mechanical engineer versus a chemist versus a physicist versus a biologist. What is standard temperature? Different. Okay? Ridiculously, stupidly obnoxious. Okay? We define this thing, STP is this value, this is what it is, this is our standard temperature, this is our standard pressure, and then somebody comes along and says, I don't like it, I'm going to make it this. That defeats the whole purpose of coming up with a standard temperature and pressure. When we're looking at standard temperature and pressure, as far as chemistry goes, what is our standard temperature? 0 degrees Celsius. How is that a standard temperature? How many reactions do we run at 0 degrees? None. Okay? Is that our standard temperature? Yes, that is our definition of standard temperature. Okay? What is our definition of standard pressure? Well, we haven't talked about pressure yet. Anybody have any guesses on standard pressure? It'll be our atmospheric pressure at sea level. That one actually makes sense. Okay? Because in general, most people are doing experiments at sea level. So we get a standard pressure. Okay? Standard temperature, I have no idea why they decided to pick 0. Depending on some, even different fields within chemistry, you'll look at other standard temperatures. Sometimes it goes to room temperature, sometimes it's 0 degrees. Make sure that you're very, very careful with what you're looking at when you're defining 22 degrees Celsius as room temperature. 22 degrees Celsius, room temperature. Okay? Which is also very odd, okay? So that's one of the reasons why we don't pick 22 degrees Celsius as our standard temperature. Okay? What is the temperature within this room? Probably not 22 degrees Celsius. Move into your lab. What's your standard temperature in the lab? It's also various or variant. Okay? So the 0 degrees happens to be an easier number to grab a hold of and pick. Okay? So, big conversion factor. This conversion factor is something that you absolutely need to be able to use and manipulate. What is the volume occupied by 1 mole of bromine gas? 22.4. What is the volume of 1 mole of nickel gas? 22.4. Okay, every single time. Why is that one a little bit odd? Would we expect to find nickel gas? No. Could we do it? Theoretically, sure, why not? And if we could, that volume, oh yeah, you could call, it wouldn't be at standard temperature and pressure. We wouldn't even be able to get to it. Okay? Why do we have to be careful with standard temperature and pressure? Okay? If we take 22 liters of gas, trap it in a container, and we heat it up. Has anybody taken a balloon and put it near some heat? What happens to the balloon? Before it pops, it expands. So when we add temperature, what happens to our volume? It changes. Okay? That's why this equation is only valid at a single temperature and a single pressure. Okay? So you have to be very careful that you're dealing with it at that single point. And you know, I know you had a question.
This with the pressure, you said it was something at sea level. What was it?
We haven't directly addressed that. We'll talk about it in a second. 1 atmosphere. It is your standard pressure unit. It's atmospheric pressure. Okay. The rest of those statements aren't a huge thing, except for the very last one on there. The force that we find from gases is what's defined as a pressure. Okay. It is the amount of energy that an individual gas particle exerts on the surface against it, or that's containing it. Okay? That is that pressure. Okay? So, before we move on with our pressure, how many liters are needed to hold 2.0 grams of hydrogen gas at standard temperature and pressure? Nice fun little conversion thing. We're going to be doing our dimensional analysis, just like normal. What do we want as our answer? We want liters of H2. Okay. And we start with what? 2.0 grams of H2. Check your units. Do your units match? No. So what do we have to do? We have to convert. So what we will do is evaluate, like we've been doing in every other case. Do we want grams of hydrogen in our answer? No. So where does grams of hydrogen need to show up? Denominator. Grams of H2. We want liters of H2. Do we have a way to relate the mass in liters? No. So we need to do some other conversion factor. Okay? So what we can try and do is shotgun effect, or if we remembered our molar volume relationship, moles can get us into liters. That's an eraser. What is the relationship between the grams of hydrogen and the moles of hydrogen? 1 mole, I like that number, is Can you say that a little bit louder? Why do you have to multiply the molar mass by 2? There's 2 hydrogens. What's the number on our periodic table? For a single atom. This is H2. That means there are 2 hydrogen atoms, which means 2.02 grams of hydrogen. Okay? What's our units now? We now have moles of H2. Is that our answer? No. What do we have to do? We need to get rid of our moles. What do we want on top? Liters. Do we have a conversion factor between those two? What's that conversion factor? What happens with our units? Moles H2 cancels. What units do we have now? Liters of H2. What answer do we want? Liters of H2. Do we have our answer? What do we do now? Put it into the calculator and solve. Yes? It depends. From what I've seen of the final, they'll typically ask for liters. They could ask for any volume. Okay? Why would they typically ask for liters? It's the easiest conversion to work with. We're trying to test you, in this case, on what concept? Molar volume. The molar volume relates moles and liters. What unit will we use? Liters. Okay? So it really depends on what the question is trying to test you on. If it's a really advanced question, we might ask for nanoliters. And then you just have to go through and convert to nanoliters. Chapter 2? Okay? Questions about that? Could we make it more difficult? Absolutely. Why not? I don't know. I have a calculator. How many liters of hydrogen are produced from the reaction of 0.165 grams of aluminum metal with dilute hydrochloric acid? What do you have to do? We need to know the amount of hydrogen produced in this equation, okay, to be able to get our answer. So what we're asking for is liters of hydrogen. What are we starting with? Do our units match? No. What do we have to do? Conversion factor. Okay. Ideally, we want grams of aluminum, and we would want liters of H2. Do we have that conversion factor? No. Okay, so now we've got a couple approaches that we could go through and do here. What I would recommend you do is notice that we are converting the substance, not just our standard unit, but also the substance. How do we convert substances? There's only one way to convert aluminum into hydrogen. Maybe push that a little bit further. You're right, it has to do with moles. It is the mole-mole ratio from the balanced equation. Is our equation balanced? No. So we'd have to go through and balance our equation. Can I do this fast? Maybe I can. Nope, I can't do it that fast. That's 3, 2... That's 6, 2, 3. Did I balance that? Okay, I think I got that balanced. We said to be able to convert between substances, we need moles, which means what do I need to convert my grams of aluminum to? Moles of aluminum. What's the relationship between grams and moles? Where do we find the relationship between grams and moles? From the periodic table.
26.98.
Okay, I'm just writing 27 because I'm tired.
I'm tired.
I thought I heard 27 actually. That's what that's my story, I'm sticking to it. We now have moles of aluminum. Is that what we want? No, what do we need to do? And we want moles of hydrogen. Is there a relationship between those two? Yes, what's that relationship? Two moles of aluminum give you 3 moles of hydrogen from our balanced equation. What units do we have now? Moles of hydrogen. What units do we want? Liters. Do we have a conversion factor between liters and moles? Yes. What is that relationship? 22.4 liters is 1 mole. So Jovan, you brought up a very good point at the very beginning. You said we needed to know the mass of hydrogen. Okay? Good idea, we got it to hydrogen. Did we need to know the mass of hydrogen? No. What did we need to know? The moles of hydrogen to be able to convert into the liters. Okay? So track your units. Maybe you need to get mass, maybe you don't. In this case, you didn't need to get to mass. All we needed to get to was moles, and then we could use the molar volume to finish off our conversion. Okay? So yet another way that we could look at our conversions, going from mass into volume. What else could we do? I could give you a starting volume and expect you to take me to an ending volume. Would this be a good question to use volume on? Can I give you a volume of aluminum? Aluminum gas? Is aluminum going to be a gas at STP? No. So this isn't going to be a good option. There are other options that you could work with. I don't remember if I gave you any on the post lab. Your textbook definitely has a bunch of questions on that too. This question ultimately is coming from chapter 9. Okay, the first one up there at top was chapter 8. That next question is a chapter 9 question. Okay, dealing with those molar volumes. Okay, whether you like it or not, I decided that we didn't want to talk about that way back when we first talked about moles. Okay, so we dealt with it now. Yes? Yes?
When you're getting an answer, you divide by 27 times.
So how do I go through and do this calculation? I'm not going to address units in this case, but I will take everything in the numerator. So I have my 0.165 times 1 times 3 times 22.4. And I will multiply all of those out to give me a number. I will then take everything in the denominator, 27 times 2 times 1, and I will get my number in my denominator. Mathematically, what do I need to enter into the calculator to get my final answer? Numerator divided by the denominator. Okay? That is personally how I would approach it instead of doing each of those multiplication divisions all the way through. That way I can limit my division errors into one spot as opposed to doing it all the way through. Okay? Other questions on using molar volume?
So it's going to be 3 significant digits?
I didn't even look at the significant digits. I have no idea on that.
For the final, will we have to worry about significant digits?
You will have to worry about significant digits on the final when you are asked to worry about significant digits on the final. Okay? So let's go back to this pressure concept. What is pressure? Okay? When we're looking at a gas, it is the force that it exerts on its environment. It's it pushing outwards everywhere else. Okay? This was not first discovered, but one of the ways it was first measured was looking at a tube of mercury. So someone filled up a tube full of mercury and then flipped it over inside a vat of mercury. What happens to the liquid inside that tube? It's going to fall, right? We put something up high, what happens to it? It falls. Okay? Turns out it doesn't fall all the way down. Okay, why does it not fall all the way down? Okay. What's happening outside the tube? Where's that liquid falling into?
The pressure it's exerting on
It comes down out of the tube, and then ultimately what happens to the volume inside the flask? It goes up. So for the liquid within that tube to stop falling, what has to happen? Something must be pushing on the outside to keep the liquid from falling out. What is that something? That is the pressure, and in this case, that is your atmospheric pressure. Okay? This gets us kind of to a new fun issue with this. Okay? We can now measure atmospheric pressure by looking at how far that mercury level dropped. Okay? The further down it drops, the less force is pushing against it. Our atmospheric pressure is lower. The further up the tube it is, the higher the pressure, because we're now pushing harder, keeping it up in the tube. Okay? So what units could we use for this? We can use at the height of the tube, or rather the height of the mercury within that tube. Okay? Since we're English or American, what units do we use? We could use inches of mercury. Okay? What if we move to the UK? What do they use, actually? Don't they use the SI system? You might get into centimeters, or maybe millimeters. Okay? Maybe we could even get into feet. Okay? This becomes one of the, in my opinion, most frustrating things when we look at pressure. Depending on what country you're in, they report the pressure differently. With temperature, it's not that bad. I mean, okay, I know the Celsius to Fahrenheit's obnoxious, but when we move into Kelvin, that one's a pretty easy one, right? Okay? When it comes to pressure, we then have to be able to convert our inches of mercury into millimeters of mercury, or into centimeters of mercury. And we now start getting all these distance measurements coming in with it. Okay? But is that the only unit we could use for pressure? What do you inflate your tires to? Pounds per square inch. The pounds of pressure per square inch of your tire. What is that? That's a pressure. What does that mean? You now have PSIs as a pressure unit. You have to be able to convert inches of mercury into PSIs. Is there another one you could use? Kind of alluded to this already. What was atmospheric pressure? Typically the one we look at is 1 atmosphere, 1 ATM. Well, what the heck is an ATM? Yet another freaking unit of pressure. So when we look at our units for pressure, we'll come back to that. We've got a ridiculous amount of them. Okay? And you have to be able to convert between those. How would you convert between those? What information do you need to know? You need to know the conversion factor. Are you expected to memorize any of these? Pretty sure you don't. I gotta check that. But I'm like 99% certain you do not need to memorize these. You will be expected to use these. So when it comes to your homework, all you're doing now is more dimensional analysis practice to try and do the conversions between each of these individual units. Treat it the same as we would convert between inches and meters. Okay? Yeah, and these pressure units will show up all over the place. The two most common ones that you'll see, pretty much the only one I'll make reference to because it's the only one that I happen to have memorized, would be the ATM unit. Why do you think I have the ATM unit memorized? It's 1. It's really easy. I have none of the others memorized. I think 760 shows up in there somewhere, but I don't know what for. There we go. Millimeters of mercury. Okay? Be aware that what you're trying to do is just kind of convert in between these. If I want to know atmospheric pressure, in the units of atmospheres, it's 1 ATM. Okay? In the units of millimeters mercury, it's 760 millimeters mercury. What's my conversion factor to go between atmospheres and 760 and millimeters mercury? 1 atmosphere is 760 millimeters mercury. What if I want to convert to PSIs from atmospheres? 1 atmosphere is 14.7 psi. What if I want to convert between millimeters mercury and kilopascals? 760 millimeters mercury is 101 kilopascals. Okay? Why do we have all of these units? Okay? My best guess is that pressure was something that was studied by a huge variety of people all around the world. All of them came up with their own particular unit. None of them wanted to give it up. Okay? And that's why we end up with a ridiculous amount of units to deal with. As far as the calculations that you will end up having to do most frequently when it comes to gases, it's 1 atmosphere. You're dealing with the unit of atmospheres. Okay? So ultimately, you always want to try and get into atmospheres. Okay? We have atmospheric pressure. We have pressure of gases. It turns out we can also get a vapor pressure, which is kind of an odd thing. That is the pressure from a liquid. But pressure is a gas thing, purely. Okay? So how do we get a pressure from a liquid? Okay? Liquids, in comparison to solids, what we've done is broke apart the intermolecular forces, holding it as a solid. So we started to rip those atoms away from each other. What happens when we move up to a gas? Now they don't interact at all. They're completely free away from each other. Liquids will naturally transition into the gas state. Okay? Is that something that you've seen already? Take a cup of water, put it on the counter, walk away, leave it alone for however many days. What happens to the water? It evaporates. It disappears. What happened? Water has a vapor pressure. The water naturally turns into its gas state. Okay? What happens if instead of just leaving it out on the countertop, we put that container of water and we now cover it? What happens to the water level? Okay? Let's try it again. Let's take a bottle of water and cap it. What happens to the water level? Thank you. It stays the same. Why does it stay the same? Okay? The gas can't escape. When we're looking at our volume of liquid changing, what's happened is some of it has turned into a gas. As long as it's now trapped as that gas, it can come back into the liquid. It goes back and forth very readily. But if we have an open container, air can flow over the top of that, and what does it do to the particles in that gas state? It allows them to escape. If they escape, now what happens? More gas fills that void. Okay? And eventually you completely evaporate everything off. What happens when we look at the reverse, trying to dissolve a gas in a liquid? Okay? How do we get the gas forced into the liquid? We put a lot of pressure behind it. You look at your sodas, what's happening with sodas? We take a canister of CO2 and we pump vast amounts of CO2 over the surface of the liquid. That CO2 then diffuses into the liquid and is now trapped inside it. Until what happens? Until we remove that pressure. And now what happens? CO2 bubbles up and we go, yippee, we have sparkling stuff. Okay? Yeah.
What would happen if you kept the bottle like upside down? Because you said it escapes up, but if it has nowhere to go, it just stay.
Well, that's what the cap does. Keeps it
So
trapped.
It would be able to go like down and out?
The arrow would come
Well-
on top.
Yeah.
But if I took the lid off this bottle and turned it upside down, what happens?
No, I'm saying like if you were to keep like a bottle of soda like this, would it stay carbonated because it can't
How-
go out? I don't know, just ask.
With the lid on it, can the gas escape?
So how does
It can't
get
escape.
flat with the lid on it?
It doesn't. When does it get flat? After you open it. Once you've opened it, you've now released a lot of that pressure. Okay, and you've lost the majority of the carbonation. When you then recap it, you now also have emptied some of the liquid, so there's now more space for the gas to fill. So the gas then fills that space and is no longer in your liquid. And that's why your sodas will go flat. You're agitating the molecules within it and causing a reduced solubility for the CO2. And so as soon as you open it, all trapped gases will do that.
I don't know if it would make a difference, but I know with soda, I've learned if you keep the cap tight, even after you open it, it stays sticky longer. I don't know.
Why would that matter? No, you're right. No, you're absolutely right. I'm not trying to make something funny there. But why does that matter?
Because the gas doesn't seep out.
The gas can't escape out the sides. So it's either closed or open. If it's open, you're going to lose the gas, period.
So in theory, if you never open it,
It would stay carbonated forever.
The same thing works if you lay it on its side, the refrigerator, as opposed to standing up, less gas escapes out.
That's true because you got the liquid as a barrier now too. Okay. One extra thing to address with this. Okay, you guys seem awfully excited about this example. I think it was that. That's cool. I can accept that. What happens when we add heat? What does heat do?
It makes it go crazy.
Causes everything to move faster. If our gas molecules now move faster, they're going to want to get out into the most space possible. Where do they have the most space? In the liquid or out of the liquid? Out of the liquid. So what happens when we heat it? The gas leaves. Yes. It depends on other factors, material properties of your bottle, but you would probably explode it. What's that? There's another, and you want to talk about that, we can talk about that too, but later. Okay? So vapor pressure. All liquids will transition into their gas state naturally. Okay? That ability to transition to that gas state is known as your vapor pressure. The higher the vapor pressure, the more likely your gas or your liquid is going to turn into a gas. Okay? Because there's now more molecules in the gas phase. That's why you have a higher vapor pressure. Okay? So if I want to dissolve a gas, what do I need to do? If I want to dissolve a gas, so it's now separately from vapor pressure. How do I get my gas into my liquid? What do I need to do? I need massive amounts of pressure of my gas. What else? What happened when I heated it? It left. So what should I do to get more gas particles in there? Decrease it. Make it cold. Okay? So if I want to dissolve more, keep it cold, put more pressure on top of it, that's going to keep those gas particles in the solution. Okay? So what happens to your Pepsi if you open it up when it's cold versus when it's hot? Yeah, it's so gross that probably people haven't tried this. If you open it up when it's hot, guess what happens? It sprays everywhere. It's going to make a giant mess. Why? You've reduced the solubility of the CO2, so as soon as you release that pressure, what happens? It goes, crap, I don't want to be in a liquid, and it immediately jumps out of the solution. In the process, it carries a bunch of liquid with it and makes a big mess.
Nobody in Arizona's left a soda can in your car.
Oh my gosh. It
Oh, yeah, there you go.
It
Yeah,
explodes.
it's seriously exploded.
let me tell you.
So don't do that either. That's a bad idea. Okay, I do need to talk about a little bit more. We did cover kind of our big ones, so I'm not super concerned about the rest, but we do need to talk about some of these. Our ideal gas behavior, we talked about one, no volume. Our particles carry no volume. Some of the other big conclusions, they travel in random directions and in straight lines. Okay? It's not exactly true, but you could even apply that to kind of humans. In general, if we look at how we travel on a much larger scale, for the most part, we do travel in straight lines. Okay? And we're using that as an approximation to simplify our calculations. Another big, huge impact when we're looking at gases is they have no attraction to one another. Okay? They're like rubber balls that hit each other and bounce away from each other. There's no gravitational field. There's no positive, negative attraction. They completely are ambivalent to each other. So if they hit, they completely bounce away. And that's one of the other things here, that when they collide, there is no loss in energy. So it's a complete elastic transition. Hit, completely bounce. Your average kinetic energy of a gas is proportional to the temperature. What does that mean? If I heat up my gas sample, what happens to the amount of energy that gas sample now has? It has more. Okay, that's about it. Okay? Let's see. Okay, so this is where we get into the variables that affect it. Your textbook goes through a whole bunch of different examples and brings in a bunch of names. Boyle, Charles, Gay-Lussac. about all these individual relationships. And then they try and give you problems about each of these on their own, which I think is dumb. Okay? What we want to go through and do is actually start to put this together. So let's think about this. Well, this isn't going to work as well because I don't have as much time. But if we have a balloon, okay, what happens if I increase the pressure inside the balloon? Okay, so let's start first with our first one. What did I just do? Could look at pressure. There's another way. I put particles into it. I increased the number of moles within this balloon. What did happen to the balloon when I added more moles? Okay, what happened to the volume? It increased. So we have a relationship between the moles and volume. Any ideas which of these symbols is moles? N. N is our mole relationship. So what we've now just found is that if I increase the amount of moles, see if we can write this down. If moles go up, what happens to the volume? Volume goes up. Okay, that's an arrow, I know. Okay, that means that these two terms are directly related. So we could set them into an equation if we wanted. Okay, that equation we'd have to be a little bit careful with because do we know exactly how much it goes up? Okay, no. Okay, so if we change the number of moles, we would expect some constant to affect this, and we could look at our volume. So when I double the moles, what happens to the volume? It doubles as well. Okay? Exactly how much, that depends on that R constant that we aren't concerned about quite yet. So now that we've got our balloon with some gas particles in it, what happens if I compress the volume of the container? Hopefully not hurting myself.
Just release it.
Well, no, we want to maintain the number of moles. What happens inside the balloon if I decrease the volume?
Pressure goes up.
The pressure goes up. We just found another relationship. Okay, thankfully the balloon wasn't that blown up. We found a relationship between volume and pressure. Okay? And that's what Boyle went through and discovered. So what is that relationship?
Volume's inversely proportional.
They are inversely related. Which means if I set up an equation, I can't say pressure or volume equals the other one. Okay? What happened when I made the volume smaller? The pressure had to go up. Which means if I said pressure here, does that equation make sense? No, that says they both go up. By saying they're inversely related, 1 over the pressure. So what happens if we now shrink this volume down and we make the pressure goes up? Okay, so now let's make the pressure a really big number. What happens to the volume? It gets smaller, exactly what we were just observing. Okay? Again, it changes with some unknown constant. That constant, in case you start to draw conclusions, okay, we should also incorporate into our equation. What happens when we look at temperature? If I try to heat up the gas in here, what happens to the volume? The volume's going to increase. All right? So we, again, now have another relationship. What happened to our volume when we increased our temperature? Our volume increased when we increased the temperature. Increase the temperature, our volume needs to expand to account for that. Okay? Again, a direct relationship. How much? I don't know, so we incorporate our R term again. What happens with our pressure? Okay? If we increase the temperature, but now don't allow the volume to change, what happens to the pressure? It goes up until eventually what happens to the balloon? It pops. Okay? So we have yet another relationship there. We've got our pressure. Whoops, I'm trying to use different colors for that. Our pressure is now going to be directly related to our temperature, again through some R constant. What happens with our moles in pressure? What happens if I keep the volume of this the same? There's no way I can do this, but I keep the volume the same and I try to blow more gas into it. what happens to the pressure? Pressure also increases. So what people were able to do is actually quantify a lot of these individual relationships.
What does R stand for?
We'll get that in just a second, I promise. So all of these individual relationships, we can now go through and evaluate each on their own using that constant, that R, some constant that allows us to convert between these two. That involves assuming that a lot of the other things don't change. Or what we could start to do is notice that there's some trends. I can relate the volume to pressure. What else can I relate the volume to? Temperature. What else can I relate it to? Moles. All of these are now interrelated to each other. So what we can start to do is attempt to organize these instead of being now in 1, 2, 3, 4, 5 different equations. I can turn all of those into one equation. That one equation is the ideal gas law. PV equals nRT. Your pressure times your volume equals the moles times some constant times temperature. What's nice about our constant? What happens if I change the temperature? What happens to the constant? It's a constant, which means it doesn't change. Right? So that's kind of a neat thing that we can take advantage of when we try and go through and solve these. I can now rearrange that equation to solve for that constant. So if I have a pressure, a volume, moles, and temperature at some starting conditions, I can now solve for the constant. What happens if I change the conditions? Okay, well now my pressure, my volume, my moles, and my temperature all change, but what happens to the constant? Stays the same. Why can that be helpful for me? What is R in both those cases? A constant, the exact same. So I can go through and start to generate relationships between these. So if I double the volume of a container and I assume everything else stays the same, I can set these two equations to each other and simplify them to relate just the pressure and the volume. Is it just pressure and volume? And I can determine that my pressure in this case would what's our relationship between volume and pressure? Inverse. So if our volume doubles, our pressure halves. You should be able to set this equation up to see that relationship. Okay? So it's kind of a neat process. You go through a lot more problems like this in the future in 151. I'll take another closer look at some of the rest of the gas slides, and we might talk about them a little bit more. There was a question on R. Feel free to pack up. I'll just keep recording. There was a question on R. R is a constant. You'll notice the most common one is 0.0821 atmospheres, liters, moles, and Kelvin. A couple big things to note here. How many new units do we have there? Or how many units do we have? 4 units. When we use R, what pressure do we need to have? What units on pressure should we use when we try and use R? It has to be atmospheres. It has to be ATMs. What volume should I use? Has to be liters. What units for temperature do I need to use? Kelvin. Okay. What happens if we change any of those units? What happens to the number? Number changes as well. There are tons of different variables or values for R. This is the most common one you'll use. And yes, I'll stop completely there.
Oh, no.